your homework 4, there are 2 questions regarding this chapter, and that's question 4 and question 5. And this chapter is pretty much standalone, but that could be the summary. In my viewpoint, it's a summary of the understanding of the dynamic systems. And again, the stability, like I made last time, for the system to be stable, and that means eventually the steady state value of the signal must be around the target. Okay, and then from there, if you remember, then we still have more classified, we more kind of define the classification of the stability. And we have the stable system, asymptotically stable systems, and the cycle, for example. So those are the behavior and observations of the system. And now we come back to here and give more quantitative description how to tell the system is stable. And the first one is by telling the locations of the poles. And stable system is all the poles. Have negative real part and no repeated root. Okay, so for stable systems, we have to fit in the 2 criteria, otherwise the system is unstable. And we can make one example here. So here we drawing is the complex plane, and thank you so much. Today we're writing, so I will slow down a little bit. Okay. So in the complex plane, we have let me make a few examples. So here, if we have 3 poles here, and basically this system is the characteristic equation is the 3rd degree polynomial equations and 3rd order systems. For this one, the system is stable. Okay, and if you like, you can make one example. Say, if you like, you can try to see if this is a -1, and here the 2 pole is -2 plus and j, and this is the -2 minus j. And for this one, the corresponding characteristic equation can be written by these. The characteristic equations for this one can be written by s plus 1 and s plus 4s plus 5. Okay, so for this one, the closed loop transfer functions, for this case, you can be written by this. For example, let me make one. In particular, this is s plus 1 and s squared plus 4s plus 5. Okay. Using these transfer functions, you can calculate its response to unit impulse, unit step, and unit ramp, and you can see the system should be stable. Okay, so that's one way to see the location like this. On the other side, from earlier we have seen for the 2 poles, its response, we have the characteristics drawing is this. If this is time, and if this is the response to unit step input, then we know this response is like this. Is the response is within the envelope, and that is governed by the exponential of the real part. And then whatever the oscillation has a frequency that is governed by the imaginary part. We know this one, we have this kind of characteristic. And for this one, the response is simply is a time. For this one, the response is simply exponential decay. Okay, so here I provide you at least 2 methods. We can tell whether the system is stable or not. And for this one, we have all the poles, negative, real part, and don't repair together, those are stable. And we can see another examples here. So this is a complex plane. If we have two poles here, and then if we have another one, for example, we have a few others on the left-hand side of the plane. And for this case, we know for this complex, this is the complex, the two poles basically symmetric and then has no real part. So that response in terms schematically is this. Basically here has no exponential decay, so its oscillation pretty much is pure oscillations of sinusoidal oscillations. So for this case, although it has one pole with a negative real part, but this one, we know this one is decaying quickly. So the response of this one corresponding is exponential decay. And furthermore, if we have, say, other poles at here, so then corresponding to this one, this pole has the oscillations response something like this one. So that means you can see for the three poles here, eventually their value will come to zero, converge to zero. So the total response of this system, which is we have 5 poles here, this is the 5th order systems. The 2 poles, the response of the two poles will govern the eventual response of the entire system. And which means you can see when we superpose the 3 responses together, eventually the response when t goes by to the large, then that response is governed by the 2 poles here. So the 2 poles are the dominant poles of the systems. And for this case, the system is still stable because the magnitude of the system when t goes large is still surrounding around the target with a finite value here. Okay, so here is although we know the area is kind of huge, but still remain finite. So here, the system we define as the marginally stable. Okay, this is the worst case of a stable system. The area is huge, but finite. Okay. The third one. The third one, let me make an example here. So, for example, here we have 2 poles, and that has on the right-hand side. So again, the characteristics drawing the response is this. This is time, and because the 2 poles has a positive real part, so basically their magnitude oscillations will be governed by the exponentially. So for example, let me make 1 and say this one is 1 plus minus 2j. Okay, so basically this exponentially is 1 times t. Okay, so we know the response will be following within the envelope, so you can see it will be like this. So this, and eventually you can see the value when t goes by large, the value is increasing. It won't be able to confine in the limit regions of the certain steady state value. So for this system, we call it unstable. Okay. For unstable system, doesn't matter how many more poles have a negative real parts, doesn't matter. As long as you can identify one pole that has the real parts, then the system eventually will become unstable. Okay, at least one pole that has the real parts, then for sure you don't need to check out the remaining. Okay. And the last one, this one will be a little bit So again, before I introduce the last one, let us review this one. This one is marginally stable, which means the two poles here, they are the imagined part. That is denoting the worst case of the stable systems. And so again, here we consider two poles here. And for example here, we have repeated poles at 0. Okay. So for repeated poles at 0, what kind of the stability of this system is, and we can see. So for this case, we know the characteristic equations is S squared equal to 0. So the closed loop transfer functions of this one is 1 over square. Okay, like this. Okay, so for example, if you want to try to solve for the let me see. So say if C over R equal to 1 over this one, then if say you want to try to solve for, say for example, the unit step response, then that will be equal to C over S will be 1 over S squared times 1 over S, and that is the S cubed. So therefore CT will be equal to 1 to T squared. Okay, so from here you can see eventually the CT is in terms of T. So in the time domain, this is the CT, the value is going up. So from here we can tell this is unstable. And for another example, if we have the repeated poles here, so let me say here. Okay, so here is the repeated poles. For example, -2 plus J and -2 plus J plus minus J. So here we have 4 poles, and they are basically repeated. So again, for these systems, we know if you solve for the differential equations, for this one you can repeat this calculation, but eventually you will see the system response will be something like the system response will be something like this. T times the sinusoidal functions exponent something like this, okay? And for this case, is stable or not? Probably we can try it. Probably we can give a try. So here maybe we can do a little bit detailed calculation here. So let me redraw that system here. So here is the real part, the imaginary part. So here we have the S1, we have the root is minus 2 plus j, minus 2 plus j, okay? So for this case, basically our characteristic equations will become like S plus 2 square plus 1 square, okay, something like this one. And so therefore, and so for example, the closed loop transferred functions and can be write by as plus 2 square plus 1 square, and say for example here numerator we after we take any arbitrary scaling factor and scaling number, for example take 1 here. So here is a closed loop, say for example C over R like this, and say we calculate for example unit impulse response. So say for example here the unit impulse response of CT can be calculated like the C here is the function of S. So CS will be equal to this one, and S plus 2 square plus 1 square, okay, times RS. And for the unit impulse, RS equal to 1. Okay. So therefore here the CT, we can take the inverse, the Laplace transform of this. And for the inverse Laplace transform, we have the table we can check out is this. Minus 1 times derivative of functions not like this. Let me pick another one. We have a table is this. If the n factorial and s minus a n plus 1, then this inverse of plus is tn and e at. And so for this case, we can try is, and also we have the, for example here is sine, and we can use this one, the s minus a square plus b square. This is e minus at sine bd. Okay, we can try to use the two properties here to solve for this one. So the first one, this CS basically is equal to, and I will try to fit into this template. So that template is this, is when we s is replaced by s plus 2. So basically I visualize this is, I do the transform, I try to transform into this one. So basically that is the form like this. Okay, so which means in this form, if we replace s by this one, then we get into this. Okay, so for this one, we have this time domain shifting. we utilize these properties. So here the CT will be equal to, the first one, this form has the inverse Laplace transform if we pick up these templates here. And this is in the second power, so when here the n equal to 1. So here is t, n equal to 1, so t to the first degree. Multiply with the exponent. For this case, here, sorry, this one is plus, and which should be in, not this one. Let me write the additional. Probably we did as is this as plus a and plus 1. This one is Tn, and this one I try to make 1. I try to make one form for this one. Do we have, right now I'm kind of stuck with
You want me to stop it?
yeah, I